Okay, good evening. Welcome to the session 7 of the parabola. And in this session, we are going to discuss the normal to the parabola. So let's write on the definition. Normal to the parabola. So let's say I have a parabola y square is equal to 4ax. And now I have a point here, say P. So this is x1, y1. And now I have a tangent also at the point P. So a line which is perpendicular to the tangent at the point of contact is said to be the normal. So we'll write in the definition here. The definition is a straight line perpendicular to the tangent at the point of contact. Now here in this case, you can assume a point. So assume Px1, y1 be a point on the parabola. Be a point on the parabola. Y square is equal to 4ax. So now I want the slope. So since you have y square is equal to 4ax1. Now we want the equation of normal basically. So I have the point here. That means if I get the slope at this point, I'm done. I know the slope of the tangent. So I can take the negative reciprocal of the slope of tangent to get the equation of normal. So I'll be differentiating this equation of normal. I'm sorry, not normal, parabola. So I have 2y dy over dx is equal to 4a. So that means from here I'll be having dy over dx is equal to 2a over y. So therefore, slope at point P, which is x1, y1, turns out to be 2a over y1. So therefore, slope of the normal. This is my slope of the normal. So slope of the normal would be the negative reciprocal of the slope of the tangent. So I have here minus y1 over 2a. This is my slope of normal. And now I have the point, this P. So by the slope point form, we can get the equation of normal. And it's much more easier to find the equation of tangent. Once we found the tangent, we already have the normal right there. So therefore, equation of the normal. So equation of the normal at P x1, y1 is y minus y1 is equal to the slope we have here, which is minus y1 over 2a. So minus y1 over 2a into x minus x1. This right here is the equation of my normal. You can leave it as it is, and in fact, you can evaluate this part whenever you want and get the equation of normal. So now, normal in the parametric form. So normal in the parametric form. So normal in the parametric form. So say I have my point P, which is 80 square comma 280. So therefore, I now will be having y minus y1 is equal to y1 is 280 over slope is again 2a into x minus x1 is 80 square. So from here I can get this 2a cancelled and I'm left with y minus 280 is equal to minus tx plus this is t here. So I'll be having a t cube. So this gives me y is equal to minus tx plus 280 plus 80 cube. So this is the equation of normal in the parametric form at point P. Okay, whose parameters are t. So now, if I compare with the standard equation of line here that we mostly use, the slope, slope intercept form. So y equal to mx plus c. So we get m is equals to minus t, and c is equals to 2at plus at cube. So if I substitute in terms of m, so I'm going to have c is equals to minus 2am minus am cube. This right here is the condition for a line to become normal. So this is the condition for line having slope m, line having slope m to be a normal. Now, one can also have the equation of normal in slope form basically, or you could say equation of the normal having slope m. So we can find out the equation of normal. So the equation of normal having slope m. The equation of normal having slope m. One can simply interchange this t with minus m. So I get y is equal to mx, y is equal to mx, and condition of normal, that is c is equal to minus 2am minus am cube. I can simply plug in here, or else you can plug in m is equal to minus t here. So this gives me y equal to mx minus 2am minus am cube. This is the required equation of normal having slope m. So whenever we're solving a particular problem and we need to assume the equation of normal, we always assume the equation of the normal to be this, that y equal to mx minus 2am minus am cube. No. So we've got this thing. Now there are beautiful properties of the normal to the parabola. Let's see them one by one, and then we'll solve some problems based on them. See. So a very important point, that normal other than the axis of parabola, normal other than the axis of parabola can never pass through the focus. Can never pass through the focus. That means if I have a normal, so if we see here, then this is the tangent at the vertex. So just now we have defined that a line perpendicular to the tangent at the vertex is nothing, at the point of contact is nothing but the normal. So we also have a normal, that is the axis of parabola, is also normal. And this is the only normal which passes through the focus of the parabola a comma 0. Rest no normal would ever pass. So we can see here. So for example, suppose if I imagine, let's say, suppose a normal passes through a parabola. I mean, suppose a normal passes through the focus of the parabola. Suppose a normal passes through the focus of parabola. Then let us see what happens. I'll be plugging here. Focus turns out to be what, a comma 0. So a comma 0 would lie on the normal. Would lie on the normal. Or you could say that normal passes through a comma 0. So I'll be having 0 is equal to am minus 2am minus am cubed. So in return we get here minus am cube is equal to 0. So I can take am common, so I get 1 plus m square is equal to 0, which in turn turns out to be m is equal to 0, and the second root is imaginary. That means m is equal to 0. So if I plug in m is equal to 0, so I get y is equal to 0, which is the x-axis. That means that's the only normal. So and suppose the normal passes the focus of parabola, we get m is equal to 0. So this implies y is equal to 0 is the only normal. Y is equal to 0 is the normal passing through the focus. Passing through the focus of parabola. So that means there won't be any normal which would pass through the focus of the parabola. Now coming to the result 2. So the result 2 is property number 2. Property number will prove it. That normal drawn to the parabola y square equal to 4ax at t1 meets the parabola again at t2. Then t2 is equal to minus t1 minus 2 over t1. What are we saying basically? So let's say I have a parabola here, and then here I have a point. So normal drawn to the parabola at t1. This normal, so I have, of course, I have a tangent there, and then I'll be drawing a parabola here. Sorry, normal. So this is the normal, and this is my pointer a t1 square comma 2 a t1, and my this normal meets here again, which is a t2 square comma 2 a t2. Then I have to prove that t2 is equal to minus t1 minus 2 over t1. So let's go ahead. So consider the equation of consider the equation of normal. Consider the equation of normal at point P at a t1 square comma 2a t1. So now I'm going to have here y is equal to, we have seen here that y is equal to minus 2a t1 is equal to minus tx. We can use this equation. So y is equal to minus tx plus 2a t1 plus a t1 cube. Now this normal meets the parabola again at t2. It's the parabola again at, we can imagine point q, say a t2 square comma 2a t2. That means this point would lie on this parabola, on this normal. So let us say this is my equation star. So therefore a t2 square comma 2a t2 lies on star. Consider this. So y is equal to, I'll rewrite the equation. So y equal to minus t1x plus 2a t1 plus a t1 cube. So therefore y is 2a t2 is equal to minus t1 into x is a t2, x is a t2. So write down here a t2 square. So that's my point a t2 square, and then plus 2a t1. So plus 2a t1 plus a t1 cube. We'll go ahead and then take this guy and this guy together. So I'm going to have 2a common, and this gives me t2 minus t1 is equal to, from here I can take a and then t1 common. So I'm going to have here, this is t1 square and then minus t2 square. So I can open this, and this a gets cancelled. This will be 2 times here. So 2 times t2 minus t1 is equal to t1 into, we can open this. So t1 minus t2 into t1 plus t2. So now since t1 is not equal to t2, that means I can cancel these two, leaving one minus here outside. So this gives me minus 2 over t1 is equal to t1 plus t2. So from here I can now get the desired relation, that is t2 we want. So t2 is equal to minus t1 minus 2 by t1. So we can keep t2 here, rest we can transfer to that side. So t2 is equal to minus 2 over t1 minus t1. This is what we had to prove. So we have proved this relation, that t2 is equal to minus 2. In fact, uh, this was another form of result. Instead of proving this way, one can simply rewrite it in this form, that yeah, here only. So I can write down here minus 2 is equal to t1 square plus t1 t2. This is far better. Now moving further,